welcome back. So, in this lecture, this is the second lecture related to Verilog HDL programming. So, in this lecture, we are going to provide some guideline for Verilog HDL programming. So, we will first talk about some rules for creating module in Verilog HDL, then some quick reference of Verilog HDL programming with examples. And at the end, we will also provide some reference material where you can get very nice detailed example and more in-depth understanding of Verilog HDL. But here we want to just summarize. So, first that Verilog case is case sensitive, that means having keywords of lower case. Then if you provide any white space, then it will be ignored. Okay, so that means if you provide space, tab, even new lines, it will be ignored. The comment, if you want to comment particular line, that means when you are writing, let's say earlier lecture we talked about any, let's say, not gate. So, suppose you are writing not b comma a, you can also give some instance. Then if you put a double line, then it will be commented. But if you want to comment maybe a few more lines, then you can use this comment. Okay. Then integral. So, that means in Verilog, if we number specification, that means if you are writing a number, whether suppose I am writing a equal to some number. If you by default, let's say this is a binary number, like a 2-bit binary number. If you this is a 2-bit binary, you can write 1001 like this. Okay, so 2-bit binary, you can write 8-bit or so on. You can also write in decimal. That means it is a 4-bit decimal, and it can take 4-bit means it can take from 0 to 999. 1000, no, I think it can take 9999, a 4-bit. 3-bit binary means it can take from all 0 to 3 ones. Then you can also have a hexadecimal number. So, you have to specify what number you are going to, but we will be using mostly binary and some cases decimal. But here I have not specified the sign number, it is just our unsigned. When you say sign, then it will be 2SB, that means sign binary, that means 2-bit sign binary, and 2-bit sign binary has a different meaning, right, because it will be in 2s complement by default, and that we will be discussing in the next week. We will talk about Q format and all. So, in this week we are mostly talking about unsigned number, more like a logical implementation. Similarly, you can have unknown as well as high impedance values and keyword. So, Verilog has some keyword which are reserved. We should not use those keyword as the variable name. So, like for example, raise value. So, this is a register value, that means it is also a reserved keyword. Now, data type. So, we have to specify what are the data type. The data can be scalar data or it can be vector data, right. That means you can talk about a scalar or a vector. Then the data can be where, that means instantaneous data you are taking, or you can keep the data stored in a register. Generally, for the input port, whenever you are taking a data, you cannot put a register, because whatever input is sending, it should directly come to your block. Okay, that means if you are connecting, let's say, one module, that means if you are talking about a half adder circuit, suppose A and B are coming, you do not know from where it is coming. It may be coming from a synchronous block, or it can be a combination logic block. So, we should not put a register here, that means it cannot be. So, it will take inside, that means the input cannot be registered, but output can be registered, or it can be in combination logic. Output is just a wire type data, there is no storing purpose. But if you are using a block where you want to store something, that means the output can be a register type also. So, register type data, that means just storing it, and this is typically used for a synchronous circuit like a D flip flop, or it can be any type of flip flop circuit like a mostly sequential circuit. And as I said, the vector data, when you write, let's say I have mentioned, and I will be taking let's say if you take a 4-bit adder, for example 4-bit adder. In case of 4-bit adder, you have a vector data which is A, vector data B, and a carry in which is a scalar, and you also have a vector output data S and the scalar C out. Now, since it is 4 bit, so we typically write 300, and for B also, that means A, it is like a 3.0, which means it is a 4 bit data, and if you take A3, this represents the MSB and A0 is the LSB. Okay. Same thing for B. B also we should write 3. It is possible you can interchange, that means you can also write A 0 into 3, that is also possible. In that case, A0, that means particularly for this case, A0 will be MSB and A3 will be LSB. So, you have to be very careful about this selection, and we generally prefer to use this type of representation, but it is possible that also you can change it. Now, integer. So, integer, that means it can be similar to register, but unlike register, it can be a sign value. That means integer, then real number. We can also take a fractional value, also real number. We can also talk about array, okay, but we do not want to initially make the thing very complex, because we will be mostly dealing with scalar and vector data. What do we mean by scalar? If the signal is only 1 bit signal, that means it is a binary 1 bit, then it is a scalar 1 bit, which can either take 0 or 1. But if it is more than 1 bit, that means 2 bit or higher, there is a vector data. That means you have multiple points and we need to take into account. Next, register and net. So, when you say this A and B, suppose we want to implement an one AND gate. So, suppose we simply implement a one AND gate, then A, whatever here it is like a B, C and A. So, this is purely an AND gate. Now, the problem is, suppose your data, so suppose what can happen, suppose if you draw the timing diagram, that means let us draw the timing diagram. Let us we are drawing timing diagram. Suppose your A data is coming, it is changing like this. So, something is changing like this. Now, B, suppose you put this is your B, but you put an identical data to C. B and C are identical, but there is some buffer circuit, that means there is some traces coming. Suppose you are putting like this. So, this is the same signal. That means B is same as C, but because there is a delay, maybe because there can be trace delay or something, C will be little shifted here. And this delay we want to avoid, because what can happen, because as if we are ANDing two signal, same signal, okay, but you can take also other signal. What I am saying, even if you take an other signal, there can be the propagation delay of, or it may be the scenario, suppose I am saying that it may be the scenario where, let us say this B, suppose B is coming from another AND gate, B is coming from another AND gate, which X and Y is the input, and it is coming like this, and A is coming from another, let us say maybe a complex function, maybe a D flip flop. Let us say you have a D flip flop Q, and there can be a reset D, and there is a clock. Now, the timing of the arrival of this circuit may differ. As a result, there is a possibility of data hazard. So, sometimes you may have to put a sequential logic, that means you have to synchronize with the clock. In that case, if you synchronize with the clock, then this after this A block you have to put a register, and that has to be updated. But if you use by default an AND gate, then it is A is a wire, that means it is just a wire connection. Whatever, whenever B and C will change, it will just make an AND operation. So that means again module declaration we have discussed, module name, list of port, then input port we have to define, output port, inside the input port whether it is a scalar or a vector, then the list of register, the list of wire. So this register can be a part of output or it can be a separate register, and we will be discussing. Suppose I am saying that we have an AND gate A and B, suppose this AND gate, C, it is going to the data input of a latch circuit. There is a clock, Q, there can be a reset. Then this data is also going out by, this can be your output. In that case the output is a register. So C is basically registered. Here C is a wire, so here it is a wire. It is an internal variable, so you have to define, because AND gate input can be directly, this is some functional block. You can think this is an IC, integrated circuit, where the terminal ports are A, B and some output, let us say some maybe Y. So these ports are outside, but this internal variable and another clock can be also output, but this internal variable is not connected to any of this port, so you have to define like a wire. Sometimes you may put another block, so after register, so you have to define which one is register and so on. So you have to declare, that means other than output. So here output itself is a register, that means here output Y, if you define, that means it is the output, you declare like a reg and it is Y. So this is a declaration that we can declare at the same instant output, Y is the output which is a register type. If you don't put register, then output will be treated as a wire output. The module declaration, module must have a unique name. Each module should be, the name must be unique. They cannot have any, you cannot have any overlap between two module name, cannot be same. Then module must not be defined inside a module, that you have told. Module can be instantiated inside a module, and the different abstractor level can be mixed together, that we have discussed. We also need to know some logical operation. So the logical operation, that means suppose, and this is particularly useful when you go to data flow modeling. Suppose I told you, that means you want to half adder, you can implement using gate level, but it may be difficult if you go further down and down, but you can use an assign statement, and these are the input A, B, S and C, where if you want S, that means suppose, or maybe you are only talking about this AND, here it is like a X, Y, Z. So here you can assign Z, X and Y, that means it will be simply AND operation. You can also have multi input addition, all these, so that means this will return as a AND, A and B. Okay. If you want to use OR, these are the symbol. So these symbols will be using data flow. So that means if we write this symbol, Verilog will understand that you are trying to implement an AND gate, and this assign will come under data flow modeling, under data flow modeling. So this will be like OR gate. So you don't have to go inside OR gate and define. So you simply write symbolically, this is OR and this is a NOT gate. That means we can write, and we have already shown that A equal to inside B, this is also a NOT operation, bitwise. The operator operation, that means this is a logical operator. The other operation like A equal to B, that means assign B to A, that means you can write assign B equal to A, which means A and B will take the value of A identically. If you write A, then if you write A double B, then if A equal to B, the output will generate one high level signal. That means this will generate logic 1. If this is true, this will lead to logic 1 if it is true, or if it is false, it will be 0. And we will be using this block in order to implement like a marking operation and other operation. Okay. Then we can, if you use this a not equal to b, that means this is the not equal to sign, not equal to sign. That means sometimes we want when a is not equal to b, that kind of symbol in assign statement or basically operator, you can use this kind of symbol, a not equal to b. And this, if you write this 3, then it is a identical to b, return 1. That means a or b are identical, return 1. And again, so these are the some of the operator, and this will operate like a bitwise. Then relational operator, because we will be using such relational operator frequently, but again we are going slowly towards the high level, because you see when you say a equal to b, we simply connect a. That means if there is an a terminal, we simply connect a wire to get b, right. So that is just a wire connection. Similarly, if we want to take whether a equal to 0, it return 1, then what to do? We can make simply a subtraction operation and take the output as the whether it is 0 or 1, right. So if all 0. Similarly, if you do a vector quantity, then we can also define bitwise operation. So we will slowly go into, but again in this course we are not talking too much about Verilog. You can go to any standard textbook and we will give you the reference link where you can learn detail, but we want to just understand some operator, because many of these operators we will be using in our code. Then it is less than, it is greater than, that means if you write a less than b, when this will be executed, this will lead to logic 1. Logic 1 if a is greater than b physically, that means if the number b is greater than a, and these are unsigned numbers. Similarly, if this is greater than, that will be true, it will return to 1 bit, and if it is a greater than equal to or less than equal to, so this can be, because we want to arrive certain condition, because we want to give, let us say we want to compare two digital number. Suppose I want to compare, let us say is like a analog comparator, right. We know the analog comparator, like it is like a comparator a and b. So this is a plus terminal, minus terminal b, and this is output y. So when output goes high, when a is greater than equal to b, then if then y equal to 1, right. If a less than b, then output is 0, else y equal to 0. So this can be realized in Verilog by writing a greater than equal to, you can say here the equal to sign will be like this, equal to b. You can write either c, or this itself will represent like a y. That means if a greater than equal to b, the whole thing will value will define as a 1, and that we call a y. So that means if you write this statement, that means if you assign, let us say you are assign use or if you want to write y equal to, it is possible, but this whole thing represents y. That means y equal to 1 when a greater than equal to b, or else it will be 0, y equal to 0, and this will identify as if like a comparator. So that means these are the comparator kind of operation, and this can be realized through relational operator. Okay, then arithmetic operation, this is also very interesting and we will be using, because we talk about adder circuit, right. So that means we want to add y equal to a plus b. This is simple addition of two number, but we have to consider this is not adder, because only addition, because we have to take care about the carry out, carry in, sum, all these we have to consider. So how does it look like? But we should remember this plus symbol indicate adder. Okay, and it can be shown that if you write assign, if you write sum comma C out is equal to two numbers, that means a plus b. which gives us that the resultant whatever will be the result, if both are like a 4 bit, you have to define this to be a 4 bit and this is a scalar. So, this is, if you have an additional carry in, you can also add C in. So, then one single statement you can actually implement the full adder, because Verilog will understand this is like a full adder, and we will be considering this also under the data flow modeling. So, that means this is an addition symbol. Similarly, we can do subtraction simply by symbol, because by this symbol actually Verilog will understand that you want to implement a full adder, and this is a concatenation operation, okay, and this symbols actually return division operation, because we will be using multiplication, division, this is like for finding remainder, but here if you want to divide or multiply, because we need to multiply proportional control with some error voltage, so we will be using simple multiplication. Otherwise, if you go for actual multiplier, then we need to define what architecture of multiplier, digital multiplier you are talking about. But since we are not talking about a new digital architecture, so we will save time. When you write multiplier, if it is implemented in FPGA, FPGA will have its some IP core which has a multiplier dedicated cell, it will assign that multiplication operation to that cell. But if you want to go for ASIC, then this multiplication has to be translated into some logic. What multiplier logic? Because there is a sequential addition, and multiplication can be divided into sequential addition plus shifting operation, right? Or it can be a direct multiplier, and which can take many clock signals, right? In fact, this multiplication is a good example which can be used to justify or differentiate between RISC and CISC architecture. In CISC architecture, the multiplier takes lot of cycle, numerous cycle to compute. That's why it is very difficult to do paralleling. But in RISC architecture, the multiplication can be divided into many summation, addition, but you need to store intermediate variable. So, then you can speed up that and you can do parallel processing very fast. And most of the ARM processor, they use the RISC architecture, so that you can do pipeline operation, you can break that into more number of smaller instruction set, so that you can reduce the each instruction cycle, and you can increase the throughput by paralleling. Similarly, you can do bitwise operation. So, these are the unary operation plus arithmetic. Then you can do bit, that means AND all bit. So, that means if you do that, suppose you have an A which is a 4-bit number. Now, I want to check if all my A are 1, then I want to assign some number. That means if all A, that means are 1, that means if it is like a 1 1 1 1, then I will say it means something. That means 1 means we want to do some task. So, this bitwise operation, what does it do? The B equal to, if you write AND of A, that means all bit of A, that means what it will do? As if it will take A3 which is the MSB, A2 next bit, A1 and A0, it will do all these AND operation as if like an AND operation, and this is your B. So, it is a bitwise AND. Okay. This kind of bitwise operations are needed when you want to perform, and we may be using this in our algorithm in future. Similarly, you can do bitwise OR, similarly you can do bitwise XOR. So, this thing we should remember, we may be using later. Similarly, you can do NAND operation, NOR operation, XNOR, all bitwise operation you can do, right? Then again bitwise AND or XNOR we have discussed. So, all these things you can get from a standard Verilog textbook. Shift operation, you can do a left shift operation. That means this shift operation is very useful, particularly if you have a binary number. Let us say you have a binary number 8-bit 8-bit binary. Suppose you have a number of 128 or something, you want to divide by 2. What do? You simply do a right shift. I think it should be the right shift, so that one bit is reduced. So that means you can reduce the number by just right shift. If you want to multiply by 2, you can do left shift like that. That means your MSB part actually expanded this side, because if you take an 8-bit number, typically what happens, we start with like a B7 into 2 to the power 7, B6 into 2 to the power 6, so on. It will go up to B1 2 to the power 1 and B0 2 to the power 0. Now if you do a right shift operation, that means you are shifting towards the right side, that means you are shifting by 1 bit, then this will become -1, this will become 0, this will become 5, this will become 6. So number will be divided by 2. Similarly, if you do left shift operation, that means you are again multiplying. So by that way you can do shifting operation. This is a concatenation operation, I told you. That means if you want to get a full adder, first is that I think the carry out will come first, then sum, then AB. So this is a assign statement. I mean, this can be used in the data flow modeling. So you can implement a full adder circuit simply by this statement. Then if you do a 3 times replication, this concatenation operation, that will explain whenever we will be using, because we need to, suppose we need to do we need to extend the bit, that means by MSB, particularly these are needed, this concatenation operation for 2s complement when you do multiplication and all. When you learn about Q format, we need this concatenation, because sometimes we will end up with redundant data. Sometimes we want to extend the sign bit, that means the value will remain same, but we can just pad with, because we want to, suppose we want to convert a 6-bit number to an 8-bit number, if it is a sign number. So you simply extend by sign bit in the MSB side, then the number will not change. So the expression and operator, that means initial operation only comes into picture during simulation. This will not be executed when you do actual hardware, because actual hardware you cannot initialize any value, because it is by default is a setup and we need to use that. Okay, so you can also use if else statement. If you use if inside a logic, if the enable is high, then buffer will be equal to data. Similarly, inside if A greater than B, that means if will be executed. If A is greater than B, it will go C equal to AB, else if it is not, then it will go to the next line. So this if and else statement are similar to our high level language like a MATLAB or C, but we should try to avoid as much as possible to use such if else statement or high level language, because we want to see the actual hardware architecture. But when these things are not possible, then we need to move. So we need to mix up between high level, that means the behavioral modeling, as well as the structural and data flow modeling. So the continuous assignment, if we go for data flow modeling, we will write assign statement, then out A and B, that means it is basically ANDed between A and B. Then if any change, that means here out is nothing but the output of an AND gate, the output of an AND gate. That means if I take an AND gate, A and B, and this is out. Since it is a continuous assignment, that means if there is any change in A, output will change, any change in B, output will change. So it will respond immediately. There is no clock synchronization here. And the left side output, this continuous assignment, left side must be scalar or vector net, but not register. So it can be scalar or vector, but it must be a wire. It cannot be a register. You cannot store, because these are wire, right? So even if you create a vector, also the assign statement, but you cannot store it. You may have to use a separate register after that, and that we will be discussing when you will deal with get signal. We want to generate dead time. So it can drive both scalar and vector values inside a net. But right side, that means if you are writing a vector y, we want to assign, like assign vector. That means we are talking about a 4-bit adder, right? 4-bit adder. So what is the input? let us say input is a 3 0 data, B also 3 0 data, C in is a scalar, C out is also a scalar, and we have a sum which is also 3b. So, in assign statement we can write assign, then first it will be C out comma S equal to A plus B plus C. As if I am assuming you have declared the input and input data as the, that means this you have declared as the input. You can write separately or put a comma. In this case, you can see the right side actually is a vector, that means here it is a vector and scalar, these are also vectors. So, that means assignment with a vector left and right is possible, but this right side, left side, it must be word type, it cannot be register, you cannot store it, but A and B can be coming from a register, it is possible. That means the data which is coming, it may be coming from a synchronous circuit, no problem. So, that means the right side can have register type data, but the left side must be scalar, sorry, it is not word type, that means instantaneous, it can be vector, but it cannot be register. Then procedural, that means you want to execute task blocking and non-blocking statement. So, when you write A equal to B, then B equal to C and C equal to D. What does it mean? That means, so A will take the value, or I will say in other way, sorry, I will say in other way. Suppose I am writing B equal to A, then C equal to B and D equal to C. This is called blocking statement. That means this will execute fast. That means the value of A, B will take the value of A. Then second will execute, C will take the value of what? B. Then the third it will take, D will take the value of C. So, as a result you will get D will take the value of A, end of this result. So, this is called blocking statement. But suppose the same thing if you write B, A, C, B and D, C. This will execute simultaneously. That means B will take the value of A, C will take the value of B which was stored earlier, and D will take the value of C. But here D is not equal to A, because we will just change the value at the level, same level. Okay, so we require such blocking and non-blocking in many cases in our algorithm, and you will get a good amount of reference in this quick reference Verilog available here. The link is provided, and you can refer the Samit Palnitkar book, and you can also refer the NPTEL course of hardware modeling using Verilog by Professor Indranil Sengupta. So, you will get more detail about Verilog. So, in summary, we have discussed some rules of creating module in Verilog, and we have also provided some quick reference of Verilog HDL programming with examples. That is it for today. Thank you very much.